So let's talk about Rutherford's alpha scattering experiment. So this was one of the early attempts to investigate the nucleus. So what they did was they used gold nucleus because gold is very stable. And how do they use to investigate the gold nucleus? Now, if you want to find out what is happening inside the nucleus, you actually try to bombard it with a known particle. So in this case, they use alpha. So alpha particle, if you know, it is actually the nucleus of helium, right? Which means to say it's positively charged. So we will direct a beam of alpha particles. So this is your source nuclear material, so a radioactive material, and it emits alpha. So we shield off every part except the front, so that alpha is coming out from the front. Alright, you don't want it to go backwards. So you just want it to go forward. So the shield is everywhere except for a small hole for these alpha particles to come out from the front. Now, after it comes out, it will actually direct towards a thin gold foil. A very, very thin gold foil. It's about in micrometers only. That's how thin it is. So why must it be very thin? Because if it is too thick, the alpha particles won't be able to penetrate. Okay, so you want it to be thin. And furthermore, this whole chamber is vacuum. So this experiment, right, they will ask you why why you do this, why you do that. So why must be vacuum? What will happen if there's air inside here? So the idea is we only want to see what happens to the alpha particle as it travels in a straight line. That means if there was air molecules in between the way, it will actually like collide with them and get deflected or slow down, right? We don't want it to happen. And after penetrating the gold nucleus, we also don't want it to be deflected by the air molecules or the or slowed down. In fact, if the pressure in this chamber is high enough, it will actually stop all the alpha particles, because alpha particles has only about few centimeters of air. Penetration is about few centimeters of air. So it may not be even able to penetrate the gap here and reach the gold nucleus. So then no point doing, right? But if it's vacuum, then alpha particles will not be stopped or be deflected by the air molecules. So it will penetrate or hit the gold foil, and Rutherford wanted to see what happens when these alpha particles hit the gold foil. Will it stop? Will it be deflected backwards? Will it penetrate? So how to investigate? He used a microscope with a zinc sulfide screen. Now sometimes you will see, instead of a zinc sulfide screen, you see a phosphor screen. Doesn't matter. It's the same function, because you see alpha particles are too small to see right now. So when the alpha particle strikes the zinc sulfide screen or a phosphor screen, it will light up. This is like producing tiny scintillations. That means it hits the zinc sulfide or phosphor screen, then it glows for a while. Understand? So that will be used to examine whether there is alpha particles in that direction. That means we'll rotate this microscope one round 360 degrees and see at each direction which direction has the most alpha particles, which has the fewest alpha particles. So how do you know when there's many alpha particles? When you see like fireworks on the screen. That means the scintillations, so many and so frequent, that means there's a lot of alpha particles. But if you just say you put to one direction, then you got one, then long time, then one, then long time, another one. These are called like scintillations, the one I'm showing. Understand? So then you will know there's a very few there. But if you put at one direction and then there's nothing at all, that means there's no alpha particles. Okay now. So what was his observation? So there are a few observations. Some of them are very important, some are not so important. Now, firstly, he was surprised to see that most of the alpha particles pass straight through undeflected. So what does it mean by pass straight through undeflected? So it means that when he placed the microscope at this direction, you notice most of them pass straight through undeflected. That means he got like so many scintillations are non-stop. That means most of them are passing straight through undeflected, as if there was nothing there. There was a gold foil there, but since most of it like hit this direction, so I was just wondering why like most of them just pass through as if there was nothing there. Okay, then the next one, which is some are deflected at angles less than 90 degrees. So you see the theta is measured from here. So as he started to rotate from here to here or from here to here, he noticed that there were fewer alpha particles coming, but still okay, still considerable amount, but of course less than the middle one, but still getting less. Then the third one, which is another important, so the one that I bold, those are the important observations that you would mention for 2 marks. 3 marks, then you probably can mention 2 of these important ones, and then 1 of the minor ones. So another one is when the angle is more than 90 degrees. So angle is more than 90 degrees means you imagine you put your microscope here. So can you see your angle here is more than 90 degrees? You'll be surprised that you will still detect a few alpha particles here. Okay, so you're wondering how come it is deflected at some angle here. In the last one, which is also a minor one, even if you put at the back here, you are also going to get, but of course it's going to be blocked by this, but theoretically, if let's say you put at the back or very close to the back, you get very, very, very few. Okay, now, so why this? So if you were Rutherford, what would you conclude? All right, there must be some conclusion to this observation. Now, if most of them can just pass straight through undeflected, but there's a goal for that. So what would your conclusion be? That the atoms must be mainly empty space. Correct or not? So then it just passes through. So that's the first conclusion. The atom is mainly empty space. So that the alpha particles pass straight through the fall with practically no deviation. Most of it most of it. Now, then the second one here, the major observation, which is this direction. So it means that some of the alpha particles actually reach the goal fall and then got repelled and go back. Or repelled and go back. So some people ask me how I know it's repelled. It could have like hit the goal fall and bounce back, right? You know, like playing pool or playing billiard, right? So if it hits something or hits a wall, it'll bounce back, right? How do I know that it is due to repulsion and not due to bouncing? Now, something you must understand now, alpha particles, if you hit another nucleus, which let's say the goal nucleus, if it actually penetrates or hits each other, it will penetrate and form a nuclear reaction. They won't just bounce back. They are not balls, they are nucleus. If 2 nucleus actually hit each other, they will actually combine and a nuclear process will take place. They will split after that. Alright, so it will not stay gold anymore. So the fact there's no nuclear reaction taking place, it means the alpha particle didn't even get to penetrate the gold nucleus. It went close and got deflected or got bounced back, repelled. So since your alpha particle, which is a nucleus of helium, is positively charged, so it means that the gold nucleus must also be positively charged. Correct or not? So alpha positive, gold must also be positive. So that is the second conclusion. The atom must contain a dense, positively charged nucleus that exerts extremely powerful fields. So the next one is we are going to learn about the path of the alpha particle as it approaches the gold nucleus. So those that are a bit further away will pass straight through undeflected. Those a bit nearer will be deflected less. Those that are even nearer will deflected more. Understand? So but you notice at which position it starts to deflect. It doesn't deflect only when it reaches the middle. It starts to deflect somewhere earlier, right? You'll notice the position where it starts to deflect is somewhere here, somewhere here, somewhere here, which is the same. Can you see that? So when you draw later on I'll show you the question. Before reaching, you must start to deflect already. And when it deflects, right, it will turn. Then after that, it will become a straight line. Similarly, it comes to here, so it curves. Then after it's a straight line. So it doesn't curve all the way like that. It doesn't curve all the way. So you just come to here, curve a bit, then it'll be a straight line. Do you understand? And the position where they deflect will be almost the same one. Okay? Now, when will it deflect up? When will it deflect down? If the alpha particle is above the middle, then it deflect up. But if it's below the middle, it will deflect down. You understand? Okay?
that's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie, we'll see you next time. Bye-bye.